In the previous class, we were looking at how to make a negative feedback amplifier, and the way we tried to do it was to take an analogy with an everyday system in which you use negative feedback, and the system we took was the way everyone drives their vehicles and tries to get it to a desired speed. Okay. That is, you are driving a motorcycle and you want to reach 50 kilometers an hour. What you will do is you will look at the actual speed. That means you sense the actual speed by looking at the speedometer. Then you compare the speedometer reading to the desired speed. That is, effectively you take the difference between the desired speed and the actual speed, and based on that you take some action which will make the motorcycle go faster or slower, and then you know that you will eventually be able to reach 50 kilometers an hour. Now what we want to get here is a mathematical description of what you are doing so that the negative feedback system works properly, and we try to do that by looking at what happens if the speedometer is stuck. Now this is easier to analyze because in this case, if the speedometer is stuck, that means that you think that the actual speed is 30 kilometers an hour, it is not changing, and the desired speed is also a constant. So the error, the result of comparison that you are acting on is a constant. So you are basically looking at what you do for a constant input. Okay. So this is easier to analyze, and this will give us insights into what kind of system we need to have here so that our negative feedback system works. And it is very obvious what you do. Let us say the speedometer is stuck at 30 kilometers an hour. So basically you think the motorcycle is going at 30 no matter what you do. So you will go on accelerating. Okay. So the actual speed will go on increasing, but you do not realize it because the speedometer is stuck. And what happens to the actual speed? It goes something like this, it goes on increasing with time. Okay. So this curve shows the behavior of the actual speed with time when you think the speedometer is stuck. Okay. Now you can get further insight into this by assuming that the speedometer is stuck at 49 kilometers an hour. I have deliberately chosen a value that is very close to the desired speed of 50 kilometers an hour. So if you see the speedometer at 49 kilometers an hour, what you do? You still accelerate so that you think you can reach 50 kilometers an hour, but in this case you do it much more gently, right. You do not actually do the same thing that you did when the speed was 30 kilometers an hour. So in this case the speed will go up gently according to the red curve here. Okay. It is still going up, but it goes at a much lower rate. So this is the behavior of the actual speed of the motorcycle with time for different values of error. Okay. So simply looking at this tells you that the action that you need is what? What is a block that gives you an increasing speed, increasing output when the input is a constant, and also the rate of increase depends on how much the input is. If the input is very small, the rate of increase is very small. If the input is very large, the rate of increase is very large. It is very obvious simply by looking at this curve. What you need here is an integrator. Okay. An integrator simply says that if there is a non-zero input, the output will go on increasing if it is positive, if the input is positive, and the output will go on decreasing if the input is negative. Okay. So that is what an integrator is, and integration is what you do. Okay. So as you are driving, you are effectively integrating the difference between the desired speed and the actual speed. I took a case where the desired speed was more than the actual speed, but if it is less, what you do is simply instead of accelerating, you go on braking until the speed reaches the desired speed. Of course, when you are driving you do not calculate the integral and so on, but that is what is exactly happening. Okay. You can take another example. For instance, let us say you are controlling the volume knob of your radio or your music player. What is it that you do? You have the actual volume which you perceive through your ears, and you have some desired level of volume, some comfortable level that you are used to. Okay. So you go on turning the volume knob, if the volume is too low, you go on increasing the volume until it reaches the desired value. that is integration. You are effectively integrating the difference between the actual volume that you hear and the desired volume, which is your idea of a comfortable level. Similarly, if the volume is too high, you go on decreasing, you go on rotating the volume knob to the left until the volume becomes comfortable. Okay. So, in this case also, if the sensing mechanism is not working, that is, let us say you lose your hearing suddenly, you will go on increasing the volume, because you do not see that the actual volume is increasing, because you cannot hear, and the volume will go on increasing with time. So, essentially the actual volume is an integration of the perceived difference between the desired and the actual volumes. Okay. So, what we need for feedback is, first of all, a way of sensing the difference between the desired value and the actual value, and secondly a way of integrating the error, integrating the difference between the desired and actual quantities, and the output should be driven by the integral of the difference. So, what happens finally is, let us go back to the complete system. So, I said this is an integrator, which I will simply denote in this way for now. The output of the integrator is the actual speed of the motorcycle or any vehicle that you are driving, and the difference between the desired and the actual is the error. So, what happens if you have an integrator? If the actual speed is different from the desired speed, it could be higher or lower. If the actual speed is lower, the error is positive, the integrator will go on increasing the actual speed. The actual speed is higher than the desired speed, the error will be negative, and the integrator will go on reducing the actual speed. Either way, the only way the integrator will stop increasing or decreasing the output is if the input happens to be 0. To have a steady state, that is to have a constant output from the integrator, the error has to be 0, and if the error is 0, what does it mean? The actual speed is equal to the desired speed, and this is again what happens in your vehicle. You will not stop until the actual speed becomes equal to the desired speed, right. If the actual speed is higher, you go on braking, if the actual speed is lower, you go on accelerating, and the only time you do not do that, you neither brake nor accelerate further, is when the actual speed is exactly equal to the desired speed. So, this system achieves the desired value by using negative feedback. It is called feedback because you are comparing constantly the actual output and the desired output, and then the way to drive the output is by integrating the error, integrating the result of such a comparison. And what we would like to do is to make a negative feedback amplifier using exactly the same principle. So, I have the input Vi and I have the output Vo, and I would like Vo to be some k times Vi, where k is the gain. And as I mentioned earlier, let us assume that Vi is DC, okay, that is, it is constant and it is not changing with time. So, what do we have to do based on the principle we just learned? We have to compare actual output to the desired output. Okay. This is what I have to do. Now, what is the actual output? The actual output is V0 or VO, and the desired output is K times Vi. Okay. So, I have to measure the error, which is K times Vi, the desired output, minus the actual output VO. Okay. This is the error, this is the difference between the desired output and the actual output. Can we do this? Now, you see an obvious flaw in this, because if I had K times Vi already, I would not be building the amplifier. The whole point of the amplifier is to take Vi and build K times Vi from it. So, I do not have K times Vi. Okay. I have Vi, from that I should generate an output VO, which is equal to K times Vi. I do not have K times Vi. If I did, I would not be building the amplifier in the first place. So, what is it that I should do? See, if you think about it, what the negative feedback system is trying to do is to make V naught equals K times Vi. It is the same as saying I am trying to make V naught by K equals Vi. Okay. That is to say, I would like to make V naught to be K times Vi, but I do not already have K times Vi, right. That is the purpose of my building the amplifier. So, which is the same as saying I would like to make V naught by K equals Vi. Okay. And this comparison I can make, that is, instead of taking the difference V naught minus K Vi, I will take my error to be V naught divided by K minus Vi. Okay. So, this is a comparison I can make, because I have the value of Vi. So, with this we have a slight extension to what we had earlier. I earlier said that you compare the actual output to the desired output. Now, it does not have to be the actual output that you the desired output does not have to be equal to, sorry. So, the output does not have to be compared to the desired output, it can be a function of the output. So, you can compare a function of the output to the input. Okay. So, that is what we are doing here. In this case, the function is simply V naught divided by K. Okay. So, this comparison I can make, and I will integrate the error to drive the output. Okay. So, I take V naught, I multiply by 1 by K. So, here I get V naught by K. I compare these two. So, here I get the error, okay, and then I integrate it. We will come to the details of the integrator soon. So, if I do this, I have my negative feedback system. Okay. And how do I get my V naught by K from V naught? That is very easy. It is a difficult thing to amplify a voltage, but it is a very easy thing to reduce the voltage. If I want V naught by K from V naught, I can simply use a resistive divider. Okay. So, let me redraw this using the actual circuit implementation of obtaining V naught by K from V naught. if I use a voltage divider like this, where one of the resistors is K minus 1 R and the other resistor is R, I will get V naught by K at the output of the resistive divider. And I subtract it from Vi and I integrate the error. I use an integrator. Okay. What will happen now? Let us say Vi is 1 volt and my K equals 5. So, I will get V naught divided by 5 here. Okay. So, let us say V naught by 5 is less than 1 volt. What will happen? The error here will be greater than 0. So, that means that the output will go on increasing. Okay. So, in this case the output will go on increasing, and the only way the output will remain constant is if this error is 0. Now, if the error is 0, the output V naught is constant if error becomes 0, and error being equal to 0 implies that V naught by K equals Vi or V naught equals KVI, which is exactly what we wanted. Okay. So, this is an amplifier using negative feedback. Okay. So, this is the basic amplifier using negative feedback, and the crucial part of it is an integrator. There are two important things. One is to be able to sense the difference, that is compute the error, and then the second thing is to be able to integrate the error to drive the output. Okay. So, these are the two essential components of any negative feedback system. We have taken an amplifier of gain K as an example, but the system is the same for any other kind of negative feedback. You control the output using an integrator to make the error equal to 0. The basic principle is that you integrate the error to drive the output. Okay. And this is intuitively similar to what you do when you are adjusting the volume control knob for your comfort, or when you are adjusting the speed of your automobile to go at the desired speed. Okay. The principle is the same. You integrate the difference between the desired and actual values to drive the output. Okay. So, now that we have the basic negative feedback amplifier, we will analyze it further, see how it behaves under different conditions. This is the integrator, and we have the voltage divider here. and I will denote this error by VE. Okay. And now we need to make the definitions more precise. First we look at the integrator. So, if you look at this integrator, it has a voltage output and a voltage input. So, for dimensional consistency there has to be a constant here which has dimensions of frequency. So, we will examine the integrator in detail, it will be clear what the role of this constant is. Okay. But before the integration you need to have a constant which has dimensions of frequency. So, we will examine this, we will see what happens when the output is different from k times Vi. We already know that the only way the output will be a constant is when the error VE is 0. When the error VE is 0, it means that V naught by k equals Vi or V naught equals kVi. So, we already know that the steady state solution to this system is V naught equals kVi, that is the output equals k times the input voltage. Okay. We also need to know what happens when before reaching steady state, that is let us say the output is supposed to be 5 volts, but it is at 4 volts. So, how does it get to 5 volts? Okay. All that analysis we will do, but before we go there we will analyze the crucial part, that is the integrator. Okay. We will see how that behaves. So, the integrator integrates the error voltage VE and as I mentioned there has to be a proportionality constant omega u, so that the dimensions are consistent. So, the relationship is V out is omega u integral VE dt. Okay. And omega u has dimensions of frequency. So, just as a numerical example, let me take omega u to be 1 gigaradians per second, that is to say 10 to the 9 radians per second. So, what happens in this case? Let me plot the output versus time, and let me assume that VE is constant at 1 volt. Okay. Let me also assume that the integrator output VO initially starts from 0. So, what will happen? The output now is 10 to the 9 radians per second integral 1 volt dt. Okay. Essentially this gives you 10 to the 9 t, and because the initial condition is 0, this is all we are going to get. So, if we plot the output at let us say 1 nanosecond, the output will increase like a ramp. So, at 1 nanosecond the output will be 1 volt, at 2 nanosecond the output will be 2 volts, and 3 nanosecond it will be 3 volts, and so on. Okay. So, if the VE is a constant, the output will increase like a ramp, will increase with a constant slope, and the slope is related to this constant omega u and the value of VE. Okay. For instance, now let us say VE becomes half a volt. What happens at 1 nanosecond? The output will be half a volt, at 2 nanoseconds it will be 1 volt, and at 3 nanoseconds it will be 1.5 volts. Okay. So, if the error is smaller, the output will rise slower, this we already know. Okay. So, that is the behavior of an integrator. If the input is larger, the output will rise faster. If the input is smaller, the output will rise slower. Similarly, if the input is negative and large, the output will fall very quickly. If the input is negative and small, then the output will decrease, but rather slowly. Okay. So, another comparison we can make is what happens if let us say I take a different integrator. This omega u is a constant that describes the integrator. Okay. It basically tells you how fast the output will rise if you apply a 1 volt input to the integrator. So, if omega u is 1 gigaradians per second or 10 to the 9 radians per second, what happens is the output will rise at 10 to the 9 volts per second, if the input is 1 volt. So, omega u is the proportionality constant. If I use a larger omega u, let us say I take a different case, omega u is 4 gigaradians per second, that is 4 times 10 to the 9 radians per second. What will happen in that case? Let us say VE, the error voltage is 1 volt. When t equal to 1 nanosecond, the output will be 4 volts. This can be easily evaluated. So, it will rise very fast. This is for V equal to 1 volt and with our new integrator. Okay. So, essentially the speed of integration is defined by omega u. Okay. So, when you get an integrator, it has a single parameter omega u which says how fast it integrates. If omega u is very large, then it integrates very quickly. If omega u is very small, it integrates very slowly. Then also the actual output of the integrator depends on this constant omega u as well as what the input voltage is. If the input voltage is very large, the integration is very fast, and if the input voltage is very small, the integration is slow. Okay. So, this is what we need to know about the integrator for now. Now, with this we will put this integrator into our system and then see how it behaves. Okay. So, we know that V naught is omega u integral V e dt. Okay. So, V I we assume is a constant. Okay. So, now we have to find exactly how V naught behaves with time. To do that, we have to write the equations describing the system, and I just substitute for V e the difference between V I and V naught by k. Okay. Now, this can be solved, but it is easier if you write this in a differential form instead of an integral form. So, that is I will differentiate both sides and I will write the derivative of output equals omega u V I minus V naught by k. Okay. So, this is the differential equation, this part here, this is the differential equation governing the system. We have to solve this equation and we will be able to see the behavior of the system, that is how V naught behaves when it is not equal to the desired value, how does it exactly get to the desired value. Okay. Now, this is a first order differential equation, and this can be easily solved for a constant Vi by rearranging the terms. So, you integrate this, solving this, what you will get is that okay, rearranging the terms, you get this. And integrating this, we will get and you have to integrate from the initial condition to the final, and here from 0 to t. Okay. So, what we will end up getting is that the logarithm of kVi minus V naught at t equal to 0 divided by the log of kVi minus V naught at t will be equal to omega u by k times t. Okay. Or if I take the reciprocal on the left side, I just negate this one. Okay. So, if I rearrange the terms of this equation, I will get V naught of t to be V naught of 0 exponential of minus omega u by k times t plus k times V I 1 minus exponential of minus omega u by k times t. Okay. So, this is the solution to the first order differential equation which governs our negative feedback system. So, what it says is the initial condition at the output decays with an exponential and the desired output grows as an exponential. Okay. So, let us first take the same example, omega u equal to 10 to the 9 radians per second, and let us say we take k equals 5, and let me plot V naught versus t. So, what does the curve look like? First, let me take the initial condition to be 0. Okay. So, in this case, the first part of the solution is not there, and we have only the second part, and we also have to specify the value of Vi. Let me say that Vi is 1 volt. So, k times Vi will be 5 volts, and if you look at this term for t equal to infinity, for very large values of t, this particular term, the second term within the brackets will become 0. Okay. So, the output will become equal to kVi, right. But for very small values of t, for t equal to 0, the exponential will be unity and the output will be equal to 0. So, what it says is the output will start from 0 and go as an exponential, that is 1 minus exponential, and finally asymptotically reach 5 volts. Okay. So, that is what happens. So, if k equal to 5, then the output will reach 5 volt when the input is 1 volt, but it starts from 0 volts. Okay. If instead it the initial condition was 2 volts, what will happen is it will start from 2 volts and the contribution of the first exponential goes on decreasing with time, the contribution of the second exponential goes on increasing with time. So, finally, we will still reach the same steady state. You can see that in either case when t equal to infinity, this term becomes 0, this term becomes 0, the output equals k V I. Okay. The steady state output is always equal to k times V I. That is what happens. So, let us say it starts from 2 volts. Okay. So, wherever you start from, it will always reach k times V I, which is the behavior that we want, but there is a period for which there is a transient, that is the output is not yet reached 5 volt, it is changing from the initial condition to the desired value. Okay. This is equivalent to the accelerating phase of your motorcycle, that is when you are accelerating, the speed is not yet the desired value, the speed is changing. Okay. Now, exactly how much time it takes we can also evaluate, we will do that shortly, but the one thing that we can tell from these expressions is that V naught of t equals k V I when t equals infinity. Okay. So, before we said that the integrator output will remain constant only if the error is 0, that is why V naught equals k V I. Now, we see from the rigorous analysis also that V naught is k V I when t equals infinity. Okay. So, we can examine some more details of this. So, as I mentioned, I will take k equal to 5 and V I equals 1 volt. So, which means that k times V I is 5 volts. So, if you start from 0, it reaches 5 volts eventually. If you start from 2 volts, it will also reach 5 volts, and if you start from a higher value, which you can do, you could for some reason start from 6 volts, you will again reach 5 volts. Regardless of where you start from, you will always reach 5 volts. Okay. Now, exactly how much time does it take to reach 5 volts? First of all, it never reaches 5 volts exactly, because these exponentials never become exactly equal to 0. Okay. They will go towards 0, but they will never become exactly equal to 0, but still we can make an estimate of when the output reaches very close to 5 volts. Okay. So, let us take a case where the initial condition is 0, the initial condition is 0, only the second part of the expression contributes to the output. So, in this case, okay, this is the output and I want this to be equal to, let us say, 99% of the ideal value, which is k V I. Okay. So, which means that this exponential should be 1%, okay, because exponential is simply the error from unity. So, the exponential should be 1%. Okay. So, what does this tell you? This tells you that T will be equal to that is 2 times natural logarithm of 10 times k divided by omega u. Note that k divided by omega u has dimensions of time, because omega u has dimensions of frequency, and this part 2 times ln 10 is about 4.6. So, within 5 time constants the output will reach 99% of the ideal value if you start from 0 initial condition. That is what the expression is saying. So, this gives you an estimate of how much time it will take for it to reach close to ideal value. Now, you can choose how close is close, it could be 99%, it could be 99.9%, but in every case you will be able to evaluate how much time it takes to reach that particular value. Okay. Now, we can evaluate the numerical example for omega u of 10 to the 9 radians per second and k of 5. So, in this case this implies that so this k by omega u turns out to be 5 by 10 to the 9 radians per second, which is equal to 5 nanoseconds. Okay. And 2 ln 10 is 4.6. So, at t equals 23 nanoseconds, output reaches 99% of the steady state or the ideal value. Okay. And here I have assumed a 0 initial condition. Okay. Now, let us say I use a faster integrator. What do I mean by a faster integrator? It has a higher value of omega u. Okay. Omega u, let us say, is 5 times 10 to the 9 radians per second or 5 gigaradians per second. So, what will happen in this case? Simply k by omega u will be 5 by 5 times 10 to the 9 radians per second, which is equal to 1 nanosecond. Okay. So, k by omega u is 1 nanosecond, and this t, instead of being 23 nanosecond, will become 4.6 nanoseconds. Okay. So, the effect of using a faster integrator in your circuit, that is an integrator with a higher omega u, is simply that the output will reach steady state faster. Now, this will be an important design criteria, in that in many amplifiers you will be told that of course, you have to make an amplifier of gain 5, but you have to reach steady state in a given amount of time. This relates to the speed of amplifiers. So, if you want to make a high speed amplifier, you need to also have a high speed integrator. Okay. So, you already see that the parameters of the integrator will influence the performance of the amplifier. So, if you can do with a slow amplifier, you use a slow integrator. If you want a fast amplifier, you have to use a fast integrator. Okay. And exactly how much also you can calculate. For instance, if you want to make an amplifier of gain 5 and it has to reach steady state within 5 nanoseconds, you know that you have to choose a unity gain frequency that is about 5 gigaradians per second. Okay. I hope all of this is clear. So, what we have learned today is first of all how to make a negative feedback amplifier. And the way to do that is to compare the divided output to the input and integrate the difference to drive the output. Okay. And from this we know that the steady state will be reached only when the error is 0 or V naught by k equals Vi, that is to say V naught equals k times Vi. We looked at the characteristic of the integrator. It has a single parameter omega u which influences the speed of integration, that is the higher the value of omega u, the faster the integration, the lower the value of omega u, slower the integration. Okay. And we also looked at how V naught changes with time. We know that the steady state solution is the steady state. In steady state the output V naught reaches the ideal value of k times Vi, but how does V naught change with time, that also we looked at. And to do that you have to solve a first order differential equation. And you will find that V naught of t has some exponentials of the form minus omega u t by k, which represent the transients. Okay. There is the steady state value of k times Vi, but in addition to that there are transients which decay as exponential of minus omega u times t divided by k. Okay. So based on this you can calculate how fast it reaches steady state. So when I say it reaches steady state, it never exactly reaches steady state, it reaches a certain percentage of the steady state. Now depending on your application you can decide how much that percentage is, it could be 99%, 99.9% or 90%, whatever it is. We evaluated some numerical examples for 99.9%. So it says that if you start with 0 initial conditions, to reach 99.99% of steady state you have to wait for 4.6 times k divided by omega u. This k divided by omega u is like the time constant of the system. And you have to wait for 4.6 time constants to be able to reach 99% of the steady state. Okay. So once you do this, the output is close enough to steady state and then you can say that it has reached steady state. We also saw that if you want to reach the steady state faster for whatever reason, you have to use a faster integrator. There is no other way to do that. If you want to reach steady state faster, you have to reach faster integrator, and this gives you a design guideline when you are designing an amplifier and you are also told that you have to reach this percent of steady state within this much time. That lets you decide how fast an integrator you have to design. Okay. So and then you go ahead and design that integrator and you will be able to complete the amplifier. So that is it for this lecture. So we have looked at how the output changes when the input is a constant. In the following lectures we will also analyze what happens when the input is changing.